Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is First Derivative Test and such. And please remember that you are in control of the throttle and the transmission for this presentation. Be an active learner. By way of motivation, the U.S. Department of Energy and the Shell Petroleum Company, the development arm of them, published this graphic that shows that going too slow or going too fast reduces the efficiency of your car in terms of miles per gallon. So you see, when you go from 0 up to around 40 miles per hour, the faster you go, your mileage increases. And after that, your mileage decreases. And the best mileage happens up here around 42 miles per hour. That's what we're going to be talking about in this lecture. So we say a function is increasing on an interval AB if, when x gets bigger, y gets bigger. So from A to B, as we go from A to B, when x gets bigger, y gets bigger. You're walking uphill if you were walking along the curve. Similarly, we say a function is decreasing on an interval AB if, when x gets bigger, y gets smaller. So you see from AB we're decreasing here. So as x gets bigger, y gets smaller. We're walking downhill on the function when we're going from A to B. And if we think about this, then that means that if the function is increasing, like this one, the blue one, the tangent line to the curve, any place where it is increasing, is going to have a positive slope. Similarly, if a function is decreasing, any place we draw the tangent line is going to have a negative slope. So this is the theorem that we're not going to prove here, but if something is increasing, f prime is greater than 0. If something is decreasing, f prime is less than 0. And if f prime is equal to 0, it is changing direction. And that means it's a constant at that instant in time. So let's look at an example. Let's find the interval where the function y equals f of x equal x squared is increasing, and the interval where it is decreasing. Well, from what we just learned and the fact that this is a differentiable function, then what we can do is we can look at the derivative of this. So the derivative of y equals x squared is y prime equal 2x. And so we say, when is it positive? So we set 2x bigger than 0. We divide both sides by 2, and that's when x is bigger than 0. Similarly, we can say, when is it negative? 2x is less than 0. If x is less than 0, dividing both sides by 2 again. So f is increasing on the interval 0 to positive infinity, and decreasing on the interval from minus infinity up to 0. Notice that these are open intervals. Now, and here's a picture of that, and you can see we have a negative slope here and a positive slope here. Recall that the graph of a continuous function cannot have breaks. As a consequence, a continuous function cannot change sign, S-I-G-N, unless it equals 0 for some value of x. And this is part of the intermediate value property for continuous functions that we talked about previously. This observation suggests the following procedure for determining the sign of the derivative of a function f, and hence the intervals where the function is increasing or decreasing. Again, this relies on the fact that the derivative is a continuous function, and that was the intermediate value theorem that we talked about earlier. Okay, so here's how we can determine the intervals where a function is increasing or decreasing. First, we find all values of x for which f prime of x is equal to 0, or where f prime is discontinuous. those will be breaks in the function where the SIGN, the sign, can change. And identify the open intervals determined by these numbers. And then we select a test number in each of those intervals that were found in test 1 and determine by evaluating the first derivative at a point in that interval if it is increasing or decreasing. If f prime at c is bigger than 0, it is increasing. If it is less than 0, it is decreasing. Let's do an example. Determine the intervals where the function, this is x cubed minus 3x squared minus 24x plus 3 is increasing, and where it's decreasing. We're following that recipe again. So the first thing is we'll take the derivative of f. Now the derivative of this function then is going to be 3x squared minus 6x minus 24, and we're going to want to solve when is that equal to 0 or when is it discontinuous. Well, it's continuous everywhere because it's a polynomial, and so we're going to factor it. So we factor this in this way. It is 3 times x plus 2 times x minus 4. And therefore, those are the zeros, and that breaks the number line into 3 intervals, from minus infinity up to minus 2, from minus 2 to 4, and from 4 to infinity. And you see we can make a little sign diagram. So there's the minus 2. There is the minus 2 to 4 is shown there, and this is bigger than 4 over here. And then we're going to do test points. So in minus infinity to minus 2, we take a test point of minus 3. We substitute it in, and that is positive. So the sign of f prime at x is positive. In this interval here, in 0, when we go from minus 2 to 4, 0 is a nice test point. It is easy to evaluate. We put 0 into, again, the first derivative. We get minus 24, and that, of course, is negative. And then when we put 5, test point up here, in we get 21, and so that is positive. So that tells us that f is increasing on this interval, and decreasing on this interval. So you see it is increasing up to here, decreasing from here to here, and increasing from there on. And we're going to use this to sketch graphs later. Let's do another example. Now this, find the interval where the function y equals f of x equal x to the 2/3 is increasing, and the interval where it is decreasing. So we're going to take the derivative of this function. So that is going to be f prime of x is 2/3 x to the minus 1/3, and that's the same thing as 2 over 3 x to the 1/3 in the denominator. Now this is not defined at x equals 0, so it's discontinuous there. And it's never equal to 0 because the numerator is never 0. So that splits the real number line into two pieces. We'll go from minus infinity up to 0 and from 0 to infinity. So we'll pick a test point in each of those, and we'll pick minus 1 here, and we'll pick positive 1 here. When we pick minus 1, we get that f prime at minus 1 is minus 2/3. You can see from the graph that it is negative there, and that is minus 2/3. And so that means it's decreasing. And then we pick the other test point, and we get positive 2/3. It is increasing. So you see it is decreasing here and increasing here. So we conclude that f is decreasing minus infinity to 0 and increasing on 0 to infinity. Another example, find the intervals where the function y equals f of x equal x plus 1 over x is increasing and where it is decreasing. We follow the same recipe. So the derivative of f is f prime is going to be, the derivative of that is 1, and the derivative of this is minus 1 over x squared. So this is what we get, and we can find a common denominator, and in fact we must do that. The common denominator is x squared. Here we multiply top and bottom by x squared, and so it's x squared minus 1 over x squared. Now, this has different characteristics because sometimes it can be 0 when x is plus or minus 1, but also it is discontinuous at x equal to 0. So you see, when I draw my line, we have places where we have to check, and so we have plus and minus 1, but we also have 0. So all of these are places where we're going to have to evaluate what happens to the sign, S-I-G-N, of f prime as we go across these intervals. So we compute f prime at x at test points in those intervals. So we'll take minus 2 in this part, minus 1/2 in this part, 1/2 in this part, and 2 in this part, and we'll calculate that, and we will get f prime at minus 2 is 3/4, minus 3, minus 3, and at 2 it is minus 3/4, and so forth. So we can say what are the SIGNs. So you see what we get is positive here, negative, negative, and positive. So from the sign diagram, this one, we conclude that it's increasing from minus infinity to minus 1, and it's also increasing from 1 to positive infinity, and it's decreasing on this interval from minus 1 to 0 and from 0 to 1. Let's look at the picture. You see it is increasing here, it is decreasing here, it is decreasing here, and it is increasing here. And there's the graph that you can see, and it does work. Now note that f prime does not change sign as we move across x equal to 0. And so that tells us that we must not automatically conclude that the derivative f prime must change sign when we move across a number where f prime is discontinuous or a 0 of f prime. We have additional terminology. If the value of the function is bigger than all nearby points, we call it a relative maximum. If it's less than nearby points, we call it a relative minimum. And you see we can have a relative maximum here, a relative maximum here, but a relative minimum. And here are the definitions of those. And so a function has a relative maximum if it is bigger at that point than all points that are within an open interval of it. And it has a relative minimum at x equals c if there exists a open interval where it is less than the points in that open interval. These intervals can be very small, however. So when we look at this picture, geometrically that means there's some interval containing x equal to c, such that no point in the graph with its x-coordinate in that interval can lie above it. And so that is the largest value, and the same thing is true about the minimum. Okay, and here's kind of a picture showing relative max there, relative max there, relative max there, relative min there, and relative min there. Now, definition, we define a critical number of a function f. A critical number of a function f is any number x in the domain of f of x, and that means it has to be in the domain of f. That is important. And then there are two other possibilities. We take the values where f prime of x is equal to 0 or where f prime of x does not exist. So when we look here, we can see we have critical number here because the first derivative is going to be 0. Similarly here, and similarly here, the first derivative is 0 because it's a horizontal tangent. And here we have a place where the first derivative doesn't exist because there's an abrupt change of direction. And here is a place where the first derivative doesn't exist because it is an infinite slope. It's a vertical tangent. So these are examples of, all of these are critical numbers, but they're different kinds of critical numbers that we can have. Notice that if we have a max, the tangent is horizontal. If we have a relative min, the tangent can be horizontal. But if the first derivative is, I guess I should have said can be in those cases, but the first derivative can be negative and not have a max or min, and the first derivative cannot exist and be a max, or it cannot exist and not be anything. So there's a bunch of different possibilities that are summarized with what we call the first derivative test. So this is the procedure for finding the relative extrema, that means relative max or min, of a continuous function f. So what we do is we determine the critical numbers. So we check to see for values where it is in the domain of f and where either the first derivative is equal to 0 or the first derivative does not exist. And then we determine the critical numbers. Those are the candidate places where a max or min can happen. Then we determine the sign, SIGN, of f prime to the left and the right of each critical number. If it changes from positive slope to negative slope, it is a max. So this is a max. If it changes from positive slope to negative slope, it's a max. If it changes from negative slope to positive slope, it is a min. And if it doesn't change sign, and that's an example here, we have a positive slope and another positive slope, it is neither. The first derivative test always works. It never fails. And we'll contrast this to the second derivative test in a future lecture. But the first derivative test always works. Let's do a few examples. So we want to find the relative maxima and relative minima of the function y equals f of x equal x squared. Okay, so we will take the derivative, and this is continuous everywhere, and we know from an earlier discussion that it's less than 0 when x is less than 0 and it's greater than 0 when x is greater than 0. So it changes sign from negative slope to positive slope. That means this is a relative min by the first derivative test. Let's look at this. Find the relative maxima and relative minima of this function, y equals f of x equal x to the 2/3. And we talked about this one before. The graph is going to look like this. And so we'll find the critical numbers. Now the derivative, we already talked about this, is f prime is equal to 2/3 x to the minus 1/3. Now that's not defined when x is equal to 0, but it is continuous everywhere else, and it's never equal to 0. So the only critical number that we have is for x equal to 0. Now when we look at that, it changes from negative slope to positive slope. That means that this is a minimum at that point. Find the relative maxima and relative minima of the function. This is f of x, y equals f of x equal x cubed minus 3x minus 24x plus 32. So the derivative of this is equal to 3x squared minus 6x minus 24. And that's continuous everywhere, so we don't have to worry about it not existing, the derivative not existing anywhere, and it can factor. So when we set this equal to 0, we find that the critical values, or critical numbers, for the function f are x equal minus 2 and x equal 4. So these are the places where we have to check. And so we're going to check. So minus 2 and minus 4 so it breaks the real number line into 3 pieces, this piece, and this piece. We do the SIGN checks, and so we check this on, we use the point here of, we can take a point on the, over here it's positive, here is going to be negative, and again when I say here I mean it's the derivative, and here it's going to be positive. So that means that here you go from positive to negative. That means it's a positive slope to negative slope. It's a relative max. Here it goes from that 4, it goes from a negative slope to a positive slope. That means it's a relative min. And often I will ask you to determine what the y value is, so you have to substitute the y value in. Often I will ask you to find the coordinates. So f of 4 minus 48 is the relative minimum, and 60 is the maximum. Find the relative maxima and relative minima of this function. Again, this is a function we've talked about before. It's this picture. So we'll take the derivative. We've done that before too. It is 1 minus 1 over x squared. And we simplified that before to be x squared minus 1 over x. And so now we have three critical points. Plus and minus 1, because that is when the numerator is equal to 0. And now this really isn't a critical point, though, because x equals 0 is not in the domain. So really only two critical numbers, and it's plus or minus 1. So what we do is we look at the sign, and we see that when we pick certain values, that it's positive here, it's negative here. That means the slope is positive, and then it's negative. That means that is a relative max. And going from here to here, we see that it goes from being a negative slope to being a positive slope, and so that is a relative minimum. Life is a word problem, and we do a lot of word problems. So here the profit function for this company is given by this equation. X is in dollars, and the profit is in dollars, Y is in dollars, and X is the number of models of these speakers that it produces. So find the profit function where it's increasing and where it's decreasing. Well, we take the first derivative of this, and we're going to say that that's always continuous, and we set it equal to 0, and we solve, and we get that x is 7,500. And so you see this derivative is going to be negative when you are more than 7,500, and it's going to be positive when you are less than 7,500. Here's a picture. These are thousands of units, and you see that the slope is negative here, and it's positive here. And so it is increasing up to 7,500, and it's decreasing after that. And these are the answers in interval notation. Another word problem, here crime rates. And so this is the graph of the crime rate function. You see it is a cubic for 0, less than or equal to t, less than or equal to 7. N of t is the number of crimes committed in the year. And t equals 0 corresponds to 2003. And where is the function increasing and where is it decreasing? Well, when you do this, what will happen is you'll take the derivative. That's always continuous. And when you look at this, you can tell that it's bigger than 0 every place in this interval. So this function n is increasing throughout the entire interval. Unfortunately, crime is always increasing, it seems. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.